Okay, so this is a tutorial for matrix analysis of truss member. Our example in the last lecture is this one. You have a three-member axially loaded truss with the corresponding force of 60 kilonewton acting horizontal and negative 50 kilonewton acting downwards. Okay, so we have three members. Therefore, we need to have three stiffness matrix. Okay, so this is the stiffness matrix for member 1, stiffness matrix for member 2, and then this one is stiffness matrix for member 3. Okay, so how do we get that? So first set up the values for elasticity, the area, the theta or the phi angle, the area of each member, and then the length. Okay, according to this uh, if this stiffness matrix here. Okay, our stiffness matrix in the global sense is this one: 4 by 4 cosine square phi, sine phi, cosine phi, negative cosine square phi, negative sine phi, cosine phi, so on and so forth. Remember, the stiffness matrix of an axial member is symmetric and a square matrix. So what I have here will be this. For example, what's the cell address of this one? This is 1, 2. First column, first row, second column. First row, second column. So that is equal to 2, 1. Second row, first column, right? This one is 1, 3. Okay. First column, first row, third column. Okay. Will be equal to 3, 1. Third row, first column. Okay. Okay, next. So you have to to make a matrix here, okay, utilizing these formulas. So for example here, cosine square, right? This one, sine phi cosine phi, okay. This one is cosine square, okay, cosine square, and have this negative sign here, okay, so on and so forth, okay. So for example, for the member 1, right, this one has a horizontal distance of 3 and then a vertical distance of 4. So I'll input the length as 5,000, 345. Its area is 4,000. Its theta is 53.13 degrees. Okay, and our E is 200,000. Okay, because megapascal. Okay, then mm square. Okay, mm square. Then mm, and then E for Newton square. Okay, so I'll have this, okay, according to this. Then this one is the final global stiffness matrix, okay, because it now incorporates the value of AE over L and then the matrix here. Okay, okay, so this is now our stiffness matrix for member 1. And what I will do is I'll copy this. Okay, copy this, Control C. Okay, where's that? So Control, oh wait, I need to copy this first, then Control C. I know, option multiple worksheets. Okay, okay. Control C. Okay, and then copy base values here. Okay, so Alt ESV or copy paste values. Okay, then okay. Okay, so this is now my stiffness matrix for member 1. So I'll do the same process again for member 2. This is now 90. This is now 5,000. And the length is only 4,000. Okay. Then copy paste again this one. Control C. And paste here. And then lastly, for member 3, length is 5,000, area is 4,000, data is negative 53.13. Alright, so Control C, then paste values. Okay, okay. So once I establish that, okay, then it's time now to formulate our structure stiffness matrix. Okay, so press escape first. You also have the option to repeat this this block depending on the number of members you have. Okay, it's just my easiest way to to create the structure stiffness matrix. Okay, so it's your discretion to create different block for each member. For example, if you have 4 members, so you will be doing this repeatedly for 4 times. Okay. Okay, so once I have established the structure stiffness matrix, okay, by what formula? So as if you may recall in our lecture, this one will be the code number for this one is 34, right? 34, 34. Therefore, that means every 34 in this K will be required to establish our structure stiffness matrix. For example, here, the code for member 1 is 1, 2, 3, 4. 1, 2, 3, 4. That's the code we have for member 1. Okay, so with that, I will be needing this code. No? Because 3, 3, 4, 3, right? 3, 4, and then 4, 3. Okay, so I'll be needing this cells here. Okay, make it blue. So same case with the member 2. I'll be needing this one. Okay, and this one. So then, in short, these cells here will constitute our S matrix. Okay. You notice that here is this one came from this plus this plus this. So therefore, its value is 0. While this one came from this plus this plus this. Okay, consistent with our coding. Okay. Okay, so I'd like to. So if you may recall, our code there is something like shapes. Okay, remember this one. Okay, Control C, Control V. Then for member 2, this one. And for member 3, this one. Right? Okay. Okay. So our code here is 1 and 2. Our code here is 3 and 4. Our code here is 5 and 6. So same here, 3, 4 also. While here is 7, 8, and also 3, 4. Okay. So they will be sharing the same code number. Okay, that's it. So once we establish S matrix, we need to get its inverse. Okay, S matrix inverse, the formula is this one, mean verse. Okay, first you need to establish a 2 by 2 array or matrix. So I'll select this one, then type in inverse, then open parenthesis, select the S matrix, then close parenthesis, and then take note, you should press Control Shift Enter. Alright, so to get the inverse of the matrix, I'll repeat. Okay, so this one, okay, then type in Control Shift Enter. Okay, why is it not working? I'll repeat this, Control Shift Enter. Control Shift Enter. Yeah, that's it. So this is now the matrix inverse. Okay. Then establish the P matrix, this one, which is 60 kilonewton horizontal and negative 50 kilonewton downwards. To get the displacement, okay, multiply the inverse, the S inverse to P. Okay, that's why prepare a 2 by 1 matrix, then type in M mult, then open parenthesis. This corresponds to S inverse, and this one corresponds to the P matrix. Okay, then same case, Control Shift Enter, and there you go. That's our displacement at code 3 and displacement at code 4. Right, so 0.52 mm horizontal and negative 0.11 mm vertical. Okay, so this node will be displacing 0.52 mm horizontal and negative 0.11 mm vertical. Okay. Now to get the member and forces, we will apply this formula. F equals kV. That means multiply the K matrix of each member, this one, to the corresponding global displacement, which we get this one, right? What is V matrix? The V matrix is this one for member 1, right? You will notice I have 0 values here because code 1 have 0 displacement. Code 2 has also 0 displacement because it's pin connected. Pin connected, code 1 and 2 is pin connected, therefore 0 displacement there. And then type in the values of what we get here. Okay, 0.52 and negative 0.11. Okay, then apply the formula F equals kV. So as you will see, I'll select this. So this is our K matrix, right? Selected. And this is our V matrix or the displacement, which is this one. And same procedure, Control Shift Enter. Okay. And that is now your member and forces for member 1. Okay. And this is again consistent with our coding. This one is for code 1. That means horizontal force at code 1, 21.56 kilonewton. While this one is the vertical force at code 2, which is our reaction. See? The reaction in STAAD also. How about for member 2? For member 2, this is 27.5 kilonewton corresponds to code 6, which is the vertical. Okay, and for member 3, applying the same concept, this corresponds to the horizontal force or reaction at member 3, 38.44 or 45 kilonewton. And this one is the vertical reaction at member 3. Okay, so that's it.